Hi everyone, I welcome you all in the 10th lecture of Stoichiometry and Process Calculation lecture for Chemical Engineering. So in previous lecture I have already described about the metal balance without chemical reaction, and I have discussed all these theory that was based on the crystallization unit as well as the evaporator unit, where I have discussed about the single effect evaporator as well as the multiple effect evaporator and how do we perform the material balance for both. And then I talked about the crystallization unit, and this is how you can perform the material balance for crystallization unit. So in this lecture today I'll be solving some problem based on that concept, and you will understand how can you use that concept in actual chemical engineering problem. So here in this problem you can see that the problem says that an aqueous solution of sodium carbonate that contains 15% carbonate by weight, and 80% of the carbonate is recovered as Na2CO3 dot 10H2O, that is a sodium carbonate decahydrate, right, by evaporation of water and subsequent cooling at 278 Kelvin. So the solubility of Na2CO3 is given to you at 278 Kelvin is 9% by weight. On the basis of 100 kg of solution treated, determine the following: the quantity of crystal form and the amount of water evaporated. So first I have told you, so you have to make some kind of schematics first, right, for this. So let's say you have a crystallization unit here, and just now what I have told you, you in crystallization unit you have a feed, right, you have a product, you have this stream, and you have this stream. So you have four stream, right? So this one is feed, right, and this one is your mother liquor here, L, and this one is, let's say, product, and this one is the water evaporated, right? So in feed the problem says 15% carbonate by weight. So here it is 0.15, right? So if I'm assuming feed is your 100, right, and then the solubility of Na2CO3 is also given to you, that is 9% by weight. Is that clear? Yeah, so here this one is mother liquor. I'll denote it as M, so this will be very easy for you. And this is product. So in mother liquor the solubility will work. So this is your 0.09. In product, the carbonate recovered as Na2CO3 dot 10H2O. So this is decahydrate, right? So here it is formed as a Na2CO3 dot 10H2O, right? Na2CO3 dot 10H2O. So this is called as your crystal, right? The product that is being formed here, that is called as the crystal. So let's say here this mole fraction I will write here. Let's say XF is your 0.15, XW of the solute will be 0 here, XM you get to know 0.09, and what would be the value of XP here? So first of all you have to calculate the value of XP, that is mole fraction or mass fraction of solute in crystal. So if I want to calculate the value of XP, so XP will be your weight of Na2CO3 divided by weight of H2O, right? So weight of NO2CO3, that is equals to 106, and then weight of water is 18 into 10, that is for weight of this one, that will be equals to 106 plus 18 into 10. So once you do the calculation here, it will be 106 divided by what? 286. Once you do the calculation, you will be getting 0.3706, something like that. Great. So now next thing is that what I have told you, I told you apply overall balance. So feed will be equals to what? Mother liquor plus water plus product. So let's say this is equation first. Now second thing is that apply if I perform the solute balance, I can say that F into XF that is equals to M into XM plus W into XW plus P into XP. So here XW will be 0. So you will be getting F into XF that is equals to M into XM plus P into XP. So F is your 100 and then you will be getting that is 0.15, right? That will be equals to the value of M we don't know. Is that clear? And then M into 0.09 plus P into M multiplied with 0.09 plus P multiplied with 0. How much we got the value? 0.37. Right. So let's say I am assuming this one is my equation second, this one is my equation first. So here you will be getting what? F that is equals to 100 that is equals to M plus W plus P. This is our equation first. Is that clear? And then in the problem it is also telling that carbonate by 80% of the carbonate is recovered as this kind of crystal, right? So what is happening here? So the problem says that 80% is getting recovered as a crystal. So what? P into XP that is equals to 0.80 into a feed into XF, F into XF, right? So if you calculate P into XP, you will be getting 0.80 multiplied with F into XF is how much? 15. So the value here that you will be getting is equals to 12. So P into XP, the value that you are getting here is that one. So now once you substitute these things, then you will be getting 15 that is equals to M multiplied with 0.09 plus 12. So the value of M you will be getting that is equals to 3 divided by 0.09. So that is equals to 300 divided by 9. So this is 100 and this is 3. So this is 33.33 kg approximately you will be getting this value. Is that clear? Now once you get the value of M, now you are supposed to get the value of P as well, right? And P into XP already you know that is equals to how much? 15. So the value of XP you know, so the value of P that can be calculated, that is 15 divided by how much? 0.3706, something like that. So you do the calculation and you will get something. Is that clear? So from here you will be getting the value of P. So once you got the value of M, you got the value of P, you can calculate the value of W as well, right? So I mean this is very simple thing. You just have to include all the concept, all the material balance what I have told you. First you have to perform the overall balance, and in the when I was talking about how steps for solving the material balance problem without chemical reaction, there I have explained to you that first you need to understand what kind of data that is being given in the problem. So you have to jot down these things. So definitely you will get some kind of clue. So here you have seen that 80% of the carbonate is recovered as a sodium carbonate decahydrate, right? So this is very important point. So if you are not able to recognize these things, then it will create some problems. So that's why you have to understand these things. Is that clear? Okay, great. So now moving towards the next problem here. So next problem is based on your evaporator, right? So in theory, I talked about the forward feeding evaporator or multiple effect evaporator. So here there is a backward feeding evaporator. So you see a triple effect evaporator is used to concentrate 1000 kg of solution from a concentration of 20% that is given here to 80% that is the product, assuming an equal amount of vapor in each effect. So here vapor in each effect is same. Calculate the composition and weight of the solute entering in the second and third effect. So you are supposed to calculate the composition and weight of the solution entering, right? So if you see here, the solution which is entering in the second, that is L1 and X1 you have to calculate, and L2 and X2 you have to calculate. So this is X1 and this is X2. So in this particular problem you have to calculate L1 equals to what, L2 equals to what, and again X1 equals to what, X2 equals to what. So it's a very good question, just try to understand. So if I perform the overall material balance first, for overall material balance, what you will see that the feed F that will be equals to how much, that is vapor plus vapor, V plus V plus V plus L3. That means F will be equals to 3V, F will be equals to your 3V plus L3. Let's say this one is my equation first. Once you do these things, then you will move towards the next thing, right? Now I'll perform the solute balance. So F into XF that is equals to V into XV plus V into XV plus V into XV plus L3 into X3. So XV is 0. Obviously there won't be any solute in the water vapor, so you will eventually left with F into XF that is equals to L3 into X3, and you know the value of F that is equals to 1000, and XF is also given to you, that is 0.20. L3 you don't know, but again the composition of these things is given to you, X3 that is your 0.8, right? So from here you can calculate the value of L3 that is equals to 250 kg, right? So the value of L3 you get to know there is a 250 kg. Okay, now again what we know that F equals to 3V plus L3. So F is your 1000 that is equals to 3 into V plus 250. So once you do the calculation you will be getting 750 that is equals to 3V. So V will be equals to 250 kg. So now you get to know how much amount of vapor is getting evaporated from each effect. Is that clear? Now that is fine. So now coming to the first effect again. So I'll perform the material balance in the first effect. So for first effect, let's say material balance first effect, what can I say, F into XF that is equals to L1 into X1 plus V into XV, and I can also say F equals to V plus L1. So let's say I am assuming this one is equation first and this is equation second, but here XV is equals to 0. So what I can say that F is your 1000 into 0.20 that is equals to L1 into X1. Let's say this one is my equation first. Okay. And one more thing, F you know that is equals to 1000 and V is your 250 plus L1. So from here L1 you will be getting is 750 kg. So once we get the value of L1, then we can calculate the value of X1. X1 will be equals to your 1000 into 0.20 divided by 750. So this will be something like that. So 4 by 3 into 0.20. Is that clear? So this is 0.80 divided by 3 that is equals to 0.2667. So the value of composition which is leaving from the first effect that is equals to 0.26, right? Now applying the material balance in the second effect, right? So if you see the second effect, in second effect, this L1 is coming as a feed here, V is leaving and L2 is going, right? So if I perform the material balance here, so what I can say that L1 equals to V plus L2. Let's say this one is my equation first for this, and then I can say L1 into X1, that is equals to V into XV plus L2 into X2. Since this XV is 0, so this equation will be equals to L1 into X1 equals to L2 into X2. Is that clear? And we know the value of L1 and X1. So L1 and X1 will be equals to 1000 into 0.20. So I can directly write here 1000 into 0.20, that is equals to L2 into X2, right? And from here, you know the value of L1. L1 is your 750. So 750, that is equals to V, you know that 250 plus L2. So the value of L2 you will be getting here is 500. Once you know the value of L2, you can substitute these things, that is 1000 multiplied with 0.20, that is equals to 500 into X2. So if you want to cancel it, it will get cancelled out, and finally you will be left with X2 equals to 0.40. So now in the problem you are supposed to calculate the value of what? The value of L1 that you got is how much? 750 kg. Unit is also very important. The value of L2 that you have calculated is this. Then the value of X1 that you calculated 0.2667. X2 is 0.40. So all of these things are clear to all of you. So this is how you can perform the material balance. So it's very easy, very simple. You just need to calculate all these parameters that is there in the that you are supposed to calculate in the problem. But yes, one more thing is that you have to write all the equation that can give you all these data, right? This is very simple linear equation. Only you have to solve the linear equation. There is addition and subtraction and all, and you will get the answer. Okay. So I hope there is no doubt in this particular problem. This is clear to all of you. And I'll stop the lecture here only. In the next lecture, I'll be talking about some problem based on the drying, absorption and extraction. And then I'll move towards the material balance involving the chemical reaction, where I'll be talking about, some percentage excess air used or set analysis, then I'll start discussion about the recycle, bypass and purge. So all of these topics are very, very important for the process calculation. Okay, thank you all for attending the lecture. Stay tuned, and those who have not subscribed the channel, please do like and subscribe the channel, and also share among your colleagues so that they can avail these kind of very fundamental lecture that is very important for the chemical engineers. Okay, thank you. See you in the next lecture.